Session today, the Ryznar Index, another weapon in the fight against metallic corrosion. Michael Smith has worked with recirculating water systems and institutional swimming pools for over 30 years, is both a certified pool operator instructor and aquatic facility operator instructor. Mr. Smith has extensive experience with natural gas and electrical efficiency systems for institutional pools and has designed and implemented hundreds of successful energy-saving solutions to public agencies and private pool owners throughout the western U.S. A graduate of California Polytech State University, San Luis Obispo, Mr. Smith has been recognized for his ability to clearly and effectively explain aquatic equipment operation, pool water chemistry, and swimming pool energy efficiency systems for both lay people and industry experts. We'll welcome Michael Smith.
Thank you, Brian. Good afternoon. It's good seeing y'all. Thanks for coming today. As Brian mentioned, my name's Mike Smith. I'm the Director of Sales with Norr Systems. I've been working with water for a good part of my adult life. I was an apprentice plumber, journeyman plumber, plumbing contractor. After I got hurt on the job, my own company, long story, I moved into working with high purity water. If you would have asked me 16, 17 years ago, I would have told you I know almost everything about water. Then I started working with swimming pools, and all my conceptions just went out the door. It's a very, very different type of recirculated water system. The company I work with, Norr Systems, we're an equipment provider and a service provider. We don't build pools. We supply equipment both to contractors and to end users, to agencies, to swimming pool owners. You know, when we work with an agency, it's real important that, first of all, we make sure that the right equipment gets selected for your application. Secondly, we work to make sure that equipment is installed correctly, either by you folks or by a contractor or sometimes by our service team. And then thirdly, and this is the most important thing, we want to make that equipment last forever. Unfortunately, that last one isn't quite attainable, but what is 100% attainable is that we can make that equipment last as long as possible. My presentation today is a bit different from the presentations you've listened to over the past couple days, and that I've listened to too. I'm not a scientist. I'm not a PhD. I'm not a doctor. I'm a nuts and bolts pool equipment guy, and I'm proud of it. A lot of what the world I work in is based upon empirical evidence, not scientific theory. And what I want to do is find out what works out in the trenches, and then after that, once something's working, I want to find out why it works. Very, very important. Kind of backwards from the normal scientific process, I think, but with the same goals in mind of achieving a better operated, longer lasting facility that is a better investment of my tax dollars and your tax dollars also. Along these lines, I'm always open to new evidence. Don't get me wrong, I'm very confident in what I've learned. But I always try to keep my eyes open, and I try to keep an open mind. The Reisner Index and our work with it happened along these lines. Even though a lot of the water chemistry parameters are important to maintaining a good Ryznar Index, are a little bit outside of the accepted parameters of what has been accepted for standard pool water chemistry, we found that this makes a big, big difference. And our experience has proved that to be the fact. Here's my objectives that we're going to talk about over the next 40 minutes. We're going to focus upon the practical applications of the Reisner Index for the aquatics industry. As some of you might know or might not know, The NSPF in its Pool Spa Operator's Handbook will be including a short section on the Ryznar Index in the newest edition that's coming out like right now. Also, too, I want to discuss some of these empirically based findings of what works and why it works, more of what works than the why, but I'll try to explain some of the why the best I can, that we can reduce the probability of pinholing in leaks in wetted metals and pipe. My third objective today is to lessen the fear that a lot of us have of what we consider to be high calcium levels in our pool water. Calcium's your friend. And then last, I want to share some success stories. I'll be doing this along the way of our conversation today. Some success stories that have come from us using the Reisner Index in conjunction with the Langelier Index, and how in your facility you might want to take a look if you're having problems with pinholing, reoccurring problems, and how you might want to adopt some of these in your own operating parameters. Here's my introduction to the Reisner Index. Not a good situation. For years and years, we've supplied pool equipment at North Systems. We've been in business now over 35 years. But up until about 14, 15 years ago, we did not supply pool heaters. If a pool heater had a problem, I'd call up the pool heater guy, and it was his problem, not mine. When we became a distributor of pool heaters, though, we started seeing some problems. These problems were leaks. The first one I remember was at a prestigious private university in Southern California. Their pool operator there, Damien, he was a good pool operator. He was fastidious. He maintained a Langelier Index, slightly positive 0.1, sometimes positive 0.2. He had to replace a pool heater, and we supplied that heater. Within a month of us providing that heater, our service manager, Joe, got a call from Damien. Hey, Joe, it's Damien. Hey, Damien, how you doing? Not good. I've got a leak in my pool heater. It's not in the pool heater. It's in the copper H bypass in front of that heater. Joe goes out, takes a look at it. Sure enough, in the middle of a long section, 2.5-foot section of type L copper pipe, near the top of it, though, was a leak, little pinhole squirting through. We were thinking, maybe this is bad copper. Maybe something's going on where they didn't ream it right, and so therefore we're getting some turbulence. We're getting some friction wear there. Dang heater manufacturer. So Joe got on the phone, got the heater manufacturer on the phone, said, hey, we've got a problem with your copper H bypass. We need you to pony up for replacing it, which they did. This company happens to be a pretty stand-up company all in all. So we hired a very reputable local contractor to go in and build a new H bypass. End of story, right? Nah. A couple weeks later, phone rings. Joe picks it up. Joe, it's Damien. I've got a leak again. Huh? Yeah, I've got a leak again. So Joe goes out, takes a look. This time this leak isn't near a joint, isn't someplace where you're likely to see the kind of leaks that we're used to seeing from friction wear or from poor pipe or from the other problems. And we knew the contractor, we knew the material, all that type of stuff. So Joe scratches his head. And we talk about it later that day, and he remembers on the chemistry controllers we were providing, one of the features in there was the ability, if you input the total alkalinity, if you input the calcium hardness, and you input the pool water's TDS, it will calculate out both the Langelier Index, the calcium saturation index, and also this thing called the Reisner Index. We didn't know what it was, but we took a look at it and started doing some research. And we found people who were saying that the Reisner Index was a better predictor of metallic corrosion than what the saturation index was. So we took a look at what it would take to meet a proper Reisner Index. And once again, in pool water, there's a few of the parameters that we as operators, as aquatics people have control over, meaning we can change, and some that we can't. I can't change your pool water temperature to 58 degrees to make a saturation index work. I can't raise my pH up to 8.3. I can't raise my total alkalinity up to 180. All of these things that my water district does at my home in California to make their water meet the index. We have parameters we have to stay within for our pools and our pool water to operate, to work right for our swimmers and for our operation. The one tool, the one factor that we could change that nobody cares about, swimmers, aquatic managers, calcium hardness. And to make this water reach the edge of the Reisner Index required over 700 part per million calcium. And we thought, what the heck, let's give it a try. So we worked with this university. We dosed the pool with calcium chloride, got their calcium hardness up over 700 parts per million. And Joe looked at me and said, Mike, we just gave Damien a recipe to scale up his pool heater. Well, Joe couldn't sleep for a couple weeks. We never got the phone call. 3 weeks, 4 weeks, a month, a couple months, 3 months. 6 months passed, 7 months passed, then that call came. And Damien said, hey, I've got a leak. And Joe said, hallelujah, we didn't scale your heater up. Happy guy. So this time, though, we took a look at what was going on, and we'll talk about some of the parameters for the Ryznar Index in a little while here. But what had happened, like many pool operators, Damien let his total alkalinity drop before dosing it to come back up again. And he didn't maintain it quite where it should be. He'd let it drop to 40 part per million total alkalinity, 35, 40, then dose it up to 100, then let it drop again. And it turned out during those times where he was at the low TA, he was in an aggressive Reisner Index. So the third repair, Damien paid for, or his bosses paid for. So there was an interesting introduction to this for us. But the funny thing about this, we can't see what's going on inside a pipe. Until you get the pinhole, you don't know what's happening, right? I don't have X-ray eyes. I think there are probably ways of predicting it ultrasonically, things like that, taking a look, but we don't have those tools really available for us. So it's really tempting to blame a manufacturer when sometimes it might be a water chemistry issue. And why is this happening? Why is this important to us? First of all, we build pools differently than what we did 20, 30 years ago. We have very little metal left in these pools. Let's think about it. What metal is left? If you have a wafer check valve that's metallic, there we go, right there before the pump. Your strainer basket, stainless steel. Your pump volute and pump impeller. What else is left after that? Your pool heater, if you have a metallic bypass, that bypass, the heat exchanger itself, maybe a stainless steel UV reaction chamber. But other than that, not a whole lot of metal left, and that makes a difference in all of this. Secondly, just as I've learned that every swimming pool is different in the way it operates, we have vast differences region to region to region in our water quality. That tends to make a very big difference. And couple that with the mandates that the EPA has put out there. First of all, the low lead stuff, so a lot of the brass, like for our impellers, is nowhere near as durable as it used to be. But secondly, they've mandated that we disinfect all surface water with chloramine. These chloramines are very corrosive and really kick up the corrosiveness of the water. Plus, there's been a move to standardize water quality, and water tends to be a lot softer than what it used to be. When I was raised in central Illinois, the school I went to, the grade school, had water that was so bad tasting, they decided the way to get us kids to drink more water is to chill it. So we got refrigerated drinking fountains. It didn't change the water quality. It might have changed the taste a little bit. But now that water, they treat that water. They make differences to it. And that's happened throughout our country. Southern California, where I'm based, has probably got some of the worst water quality there is. All that water is mixed up from a whole bunch of different sources. And once you think you know what you're doing with your source water, they change the source. They switch from Colorado River to the aqueduct to wells or this or that. So it's not consistent. And the other thing that isn't consistent is there's no steady state in our pool water chemistry. Our parameters, our water chemistry is constantly changing. And we don't take a look at that. So there isn't a steady state. So we're in an up and down situation, back and forth and sideways throughout the day, every week, every month, every year. So here's a thought that could keep you up at night. Your pool is filled with water that is either actively corrosive or potentially corrosive. Right here, right now. Start thinking about it. So what's this Ryznar Stability Index all about? It was developed by a gentleman, Dr. John Reisner, during World War II. Dr. Reisner was kind of baffled. He took a look at Langlier's work. Actually, Dr. Langlier, right? He was from France. But he found out that both high calcium and low calcium water could end up with the same Langlier saturation index number. So he wanted to do something about it. He changed the formula to take a look at where the pH at calcium saturation would be as opposed to where the water is right now. And he did a little bit of math, but for the same idea. These formulas, the formula that Reisner came up with and developed has been further refined many, many, many times. Pecorius and Brook in the 1980s, Stiff Davis Index, taking a look at high TDS water, and we'll talk about high TDS in a little bit here, and things like the Odo-Thompson Index that look at CO2's effect on corrosion. But the reality is these aren't really looking at corrosion. All of these indices were put together to take a look at the scaling potential or aggressiveness to scale, calcium carbonate scale, in water. None of them have to do truly with corrosion. However, there is a correlation between these indices. And it's real important to keep in mind what an index is. An index is a model. It's an ideal. They're trying to look and use a tool to make some predictions. It's not 100% there. It's a norm. It's a average. It's not consistent everywhere, every time, because there are factors outside of these indices that greatly influence water's corrosive ability. But this is what we're afraid of. This is a cutaway of an old swimming pool heat exchanger. Our industry, where's my pointer? There it is, has a very, very strong fear of calcium scaling. This comes from the days when everybody was using gas chlorine. And gas chlorine's effect upon the pH of the water was a downward effect. And so you had to use soda ash, or you had to use caustic soda to maintain your pH at the level you wanted it at. And if your caustic soda pump ran away on you, you'd end up with high pH water localized. And of course, inside of, we'll see the role heat plays inside of a heat exchanger. When the heater's on, that index goes way more towards the scaling side. So we're afraid of things like this. You know, I've interviewed a lot of corrosion experts getting ready for this, and also for my own education and my own interest. And I tell you what, if you ever have insomnia and you need to go to sleep, get a corrosion manual and start reading it. It'll put you right to sleep. But it's interesting, though, the individuals who are working as corrosion experts tend to be pretty interesting people. Some of them are funny as all get out when you talk with them in person. You would never know that from the writings, though. And A gentleman who I did not have the opportunity to talk with is Mr. Cavano. He wasn't a PhD, but he was a specialist. He started his own company. He passed away 4 or 5 years ago, unfortunately. And he actually injected a lot of humor into his writings, which is pretty difficult to do in this stuff. But here's Mr. Cavano saying that these scaling indicators were never intended to measure corrosive water. They were rather to predict calcium carbonate scaling, or if the waters would be aggressive and be hungry for calcium. They don't give any attention to some of the factors that I was alluding to, like chlorides, like sulfate content, which are some of the biggest stuff, along with amines, like chloramine, to corrosion. And he quoted Picorius, who refined Reisner's Index, saying that cooling water, and I would substitute pool water in here, is always corrosive because of the presence of dissolved oxygen and dissolved solids. This is true when the water forms scale, but also true even when it's not scale forming. So, interesting, very interesting. Once again, our fear. There's calcium oozing out of old wall return. Not a good thing. Very visual. You can see it happen. So, what's the deal with the Ryznar Index? And what are we trying to do? We're trying to minimize ion transfer of metals. What happens is inside of a piece of pipe, there could be little imperfections, microscopic imperfections even. There can be also areas where there's a little bit of suntan oil, or a little bit of body oils, or a little bit of flux left over when the pipe was soldered up that coats part of the surface of the pipe and it deprives it from oxygen. This area will become an anode, usually with a positive charge, but sometimes anodes have negative charges, go figure. And these ions from this anode will be traveling towards a cathode. A cathode's an area with higher oxygen content, with higher oxidation potential at it. So we've got an actual little plating factory going on, taking ions of metal from an anode towards the cathode. We can predict anodes. We can use sacrificial anodes, but it's interesting, even with a sacrificial anode inside of a metal tank or a piece of metal or an aluminum boat or aluminum swimming pool, often the cathode may be somewhere else, and the anode might be traveling, and the cathode might be attracting metal and not your sacrificial anode, even if it's very near it. It's interesting how all this works. So we cannot predict where these cathodes are going to be. If we were able to predict cathodes, if I was able to predict cathodes, I could probably retire. I could start going out with a cathode prediction business, but we can't do that. So we have to live with it. And it's interesting, part of the Reisner Index, what it's all about is leaving a very thin coating of calcium on the inside of your metallic pipe. That thin coating might be only, 1 molecule thick. But if it covers a cathode, it stops at attraction. If it covers an anode, it will keep the ions from traveling. And just as importantly, calcium is a metal. And that calcium itself can serve as an anode, where it will be attracted to the cathode. So we're doing 2 things with calcium in our water. We're covering cathodes potentially, and we're using that dissolved calcium in the water as an anode, both. That's a blown-up photo of a piece of galvanized pipe that is threaded that has a little pinhole in it right there, right where the arrow is. That's not the kind of stuff you want to see. It's interesting. Galvanized pipe, which used to be the norm, it only works. It only protects that steel underneath it if you have some calcium in that water. So the Reisner Index itself, I put a slide rule out, several of them out on the different tables out here. There's 2 sides to that slide rule. One side is for the Langelier Index, the calcium saturation index. The slide rule assumes that you have over 1,000 TDS. Most of our pools that we work with in the regions I work with, the vast majority are outdoor pools. And the vast majority of them are in sodium hypochlorite. And most of the pools I work with operate with TDSs of 4,000, 5,000, 6,000, 8,000, 10,000. They usually drain the water by the time it gets somewhere between 8 and 10, at least half of it, and get it down again. The slide rule itself, if you take a look at it, though, one side's calcium, this calcium saturation index. The other side is the Reisner Index. And if you look at the little TDS slot in both, just as if you look at the calcium slide on both of them, the higher you get in TDS, the higher you get in calcium, each unit becomes less significant. For instance, on TDS, if you go between, I think it's 400 and 700, that gap is as big as between 2,000 and 4,000. So the higher TDS you get, the less significant it is. The higher calcium you get, the less significant each unit of it is, as I should say. But here's a graphical scale of the Reisner Index. And it's a little confusing sometimes because the numbers sound like they're pH numbers. They're measured in, the same type of scale because we're actually subtracting the pH of the water from twice the pH at the water's saturation. And once we get higher on the scale, and this is counterintuitive as opposed to Langleyer's index, the higher we are on the scale, the more potentially corrosive this water is. Our sweet spot is between 6.3 and 6.8 Reisner Index. As we start getting higher, more and more corrosion, actually, he'd be coming here and saying, no, that's not what it's about. It's more and more aggressive towards calcium. But our experience shows that it's been more and more aggressive towards metals also. As we get lower, the more scaling we are. So here's some pool water combinations that work. First of all, if you're maintaining a Langleyer index 0.5 on the positive side, predominated by calcium, you're probably maintaining a good Reisner index also. But here's some pretty typical balanced Reisner water. pH 7, keep on hitting the wrong button. pH 7.4, temperature 80, total alkalinity around 100, calcium hardness 700 ppm, TDS 4,000. Or a little lower TA. Say if you're using Cal Hypo and you want to keep your TA a little bit lower, you've got to compensate with that. Even though our temperature might be a little higher here, a little higher calcium level, and of course something like a spa where we've got our pH a little lower to maximize our oxidation ability, but our temp's high, and we're still 450 part per million calcium. Any combination that gets you there would work, but the combinations we can use in our swimming pools focus upon us needing to have a fair amount of calcium in that water. My introduction, and from a lot of the people I work with to the Reisner Index, came through pool heaters. And in these next set of slides, not all the corrosion we're going to take a look at comes from not maintaining a good Reisner Index, but some of it does, and we'll talk about what the difference is. For instance, we've got a hole right here in the middle of this temperature well. Where's my pointer? There it is. Kind of hard to see it right there. And Nor Systems, we service over 1,000 pool heaters each and every year. We have never seen a heat exchanger scale up due to high calcium. Took us a long time to be comfortable with saying that, but I'm 100% comfortable with saying that. We have never seen a pool heater scale due to high calcium. It's always because of elevated temperatures, because you're not putting enough water flowing through that heat exchanger. So you need to keep water going through that heat exchanger the way that the manufacturer recommends, or by extremely high pHs, pHs above 8.3 that start precipitating calcium back out of the water. Obviously, if you're going to be maintaining 800, 900, 1,000 ppm calcium, you need to have good pH control. But the way that most of our pools that are nowadays either on cal hypo or sodium hypochlorite as a oxidizer sanitizer, I would argue that you could not and would not get those high pHs. The trend with our sanitizer is high, but you would notice the effect in the pool water before it started chunking up on you, the calcium. First, to be cloudy water. Secondly, if you have a decent chemistry controller, it would lock, and it's calibrated and standardized correctly, it would lock you out. So you're not going to get there. If we look inside these tubes, we see some damage that is caused by metallic ions being eaten away inside of some of these tubes in here. We're seeing also some friction wear, velocity wear on the edges of these, just as we are here. But if you look inside, once again, we're seeing areas where we're getting the type of pitting that will become a leak eventually. There's another good example right on the edge of this tube right here. There's a great example right in the middle of the run of the heat exchanger. A hole pops through finally. And as I said, keeping a good Reisner wouldn't have fixed all of this, wouldn't have prevented all this from happening. A lot of this is because maybe our pool operators aren't as diligent as what they should be. Maybe they're not as skilled as what they should be. Also, maybe you're running too much water through and we're actually getting friction wear from high velocity. Could be part of the design that's inherent in your facility, and it could be because of other factors that we're not taking a look at, chlorides, sulfates, things along those lines. There's one that gets it all. Looking inside of it, we've got pretty heavy velocity wear along the edges, but looking inside, once again, we've definitely got the type of pitting that is associated with ion movement of metals. Stainless steel is more noble, right? It seems like the least noble metal gets attacked first, but not always. It really depends. This is a drain port plug on a UV reaction chamber. Here's another look at it, looking inside of it. It's really heartbreaking to have a stainless steel vessel start leaking on you. But you know, this type of corrosion can be very, very localized. And as I said before, you could use a sacrificial anode. And we're doing that now with a lot of the UV chambers that we work with, where that drain port connects. Instead of just putting a cap on there, we're putting a cap that has an anode built into it, a zinc anode. So that tends to help, but doesn't prevent it 100%. But it does make a difference. And if you do have any of these type of problems, you might want to think about talking with your service provider or equipment provider and getting some type of sacrificial anode. Something else that we need to keep in mind is the greatest changes in liquid water chemistry, water between freezing and boiling, occur between 20 degrees Celsius and 40 degrees Celsius. Between 68 degrees and 104 degrees. What temperature do we keep our pools at? Right there. There we go. And it's interesting with water, you know, I thought, what's that all about? And water, when it gets near absolute zero, which is negative 273 degrees Celsius, 460 degrees negative Fahrenheit, things start changing. You know, all that superconductor stuff they're doing with ultra cold and all of that. But once you get a little bit above that, there's not a whole lot of changes until you get to 0 Celsius, where that ice melts. Then, of course, when you get to 100 degrees Celsius, 212 Fahrenheit, that water, liquid water, boils, turns to steam. But once it's steam, there's not a whole lot of changes in it until it gets up to being water plasma, which in ultra-pure water, has to be ultra-pure, somewhere around 700 degrees Fahrenheit, 375 degrees Celsius. That's pretty hot. So the range we operate our pools in is where we get the biggest changes in water chemistry going on along the parameters that we're looking at for corrosion. Water's interesting stuff. I've worked with it all my life. It still fascinates me the way it behaves. And we found, once again, that sites that keep a Ryznar index I'm not going to say 6.3. That's pretty hard to get there. You've got to use a lot of calcium and keep your pH up fairly high compared to where we want to operate it to get the biggest impact of our chlorine. But 6.5 to 6.7 and a Langelier saturation index positive 0.3 to positive 0.6 stops pinholing. Unfortunately, if you have a pinhole, it won't fix it. You have to repair whatever happened there. But it will stop this pinholing from our experience. We've seen this over and over again. There's another pinhole leak. Welds present a very, very interesting problem, even when they're buffed and burnished and done correctly and all that kind of stuff. It's so easy to get an imperfection in a stainless steel weld. But once again, if you're maintaining a good Reisner index along with a good Langelier index, we tend to do okay. There's some more corrosion. In fact, that's kind of interesting the way it works. We'll get a couple close-ups of that in a minute here. And it's important to keep in mind, too, that different components in our recirculation system, in our swimming pool, operate at different temperatures. And temperature drives both of these indices one way or another. The warmer, the more scaling; the cooler, the more aggressive. That's a little counterintuitive, the cooler side being more aggressive, but that's the way it works. And we do a test of our water. How often do we test for total alkalinity? How often do we test for calcium hardness? Maybe weekly. I know some of the operator books, guidebooks recommend maybe monthly on some of these, like calcium hardness. It doesn't tend to change too much unless you have a leak or splash out, because calcium, once again, doesn't dissipate or doesn't go away except for by dilution. But our water chemistry, with our swimmers in the water, with the impact of the environment, with everything else going on, we're under different conditions. And we tend to think when we write that number down, that water's going to stay there. But unfortunately, that's not the case. Pretty significant corrosion along the sides that we're looking at here, over on this side. And compared to other types of operating plants, compared to power plants, compared to pharmaceutical plants or refineries, our pools are basically unoperated for a good part of the day. We don't have somebody sitting in front of a council constantly taking a look at the parameters and making constant adjustments throughout the day. We tend to have a chemistry controller that might adjust pH, and might adjust the ORP. Maybe if you might have one that actually looks at part per million also, but we're not looking at all the other factors. And especially in my neck of the woods, we tend to have pretty unqualified pool operators. It breaks my heart. I think a lot of it in areas where they have swimming pools, a lot of the people making decisions at the agencies might own a pool themselves. If not, they have a neighbor that does. Once a week, a guy comes by with a pickup truck and a pole, adds a little, does a little, cleans the pool, and that's it. Piece of cake, right? You all know that. Isn't it an easy job? You don't have to be qualified to operate this pool. Unfortunately, that's a mindset that I work against and fight against all the time. I've actually had people that have a pool, an agency that has a pool for the first time, and they truly believe because of automation they did not even need a pool operator. All they need is somebody sweeping it every now and then. Doesn't work that way. And lots of times, we don't educate our operators as well as they should be. They might not truly be competent to make these decisions that will greatly influence your multi-million-dollar facility. And we don't take a look at a lot of things like overall water chemistry. I've talked about that a couple times. We test for a very limited set of factors. pH, chlorine content, part per million, total alkalinity, water's resistance to pH change, calcium hardness, how much calcium is dissolved in that water, TDS, how much salt metals are dissolved in that water. That's it. We don't tend to look at the big, wide scale of parameters that maybe we ought to. I had one corrosion expert tell me, I think that you need to start building $500,000 pump rooms with $500,000 worth of controls in them. So I don't think that's going to happen either, unfortunately. So we've seen this work. As long as we keep our water moving properly for our heaters won't scale up. As long as we keep our pH where we want it to be, and definitely below 8.3, we're not going to scale up. Now there's another, take a look at a stainless steel reactor, more and more of it eaten away. This site, once they put an anode in, and once they started maintaining a proper Reisner, we had to put a whole new UV chamber in there. They're not having problems anymore. And it's not bonding. It's not electrical current. Pretty nasty looking. Looks like Swiss cheese inside of there, but it should be solid stainless steel. The less noble the metal, the more probable you'll have corrosion. Think about a pump volute. That lousy brass that we have to use nowadays, it doesn't have any lead in it. Once again, the EPA, good for them for protecting the nation's health and drinking water. Doesn't work so well inside of our pump volutes. That impeller's got a lot of things that happen to it, or what used to be an impeller. It's had actual chemical damage to it too, but also this site was maintaining a Ryznar Index pushing 9. Their calcium hardness was about 110. Different view on it. I don't think they're moving a whole lot of water. Joe, our service manager, has an impeller garden, by the way, full of impellers, different sizes, different shapes, different states of decay. And here's what it looks like inside the pipe. Here's some examples. Here's a 2.5-inch brass nipple with a flange. Looking on the outside of the pipe, it looks fine, but if you look inside of it, you've got like somebody was taking a magnifying glass in the sunlight and beaming a hole through it. Mr. Spock and his phaser right there. And you don't see any of that until that little pinhole makes its way through the pipe. Here's looking inside of some Type L copper. It's a 2.5-inch by 2-inch bell reducer with pipe. Here's our 2-inch pipe here. There's the edge of the bell reducer you see on the side. Here's our 2-inch pipe. I have this photo hanging behind my desk next to the picture of my wife. So this is something that I want to make sure anytime anybody's talking with me, they see what can happen if we don't take care of our pool water chemistry correctly. Another close-up of that. So in summary, we found that maintaining a Ryznar index between 6.5 and 6.7 in conjunction with maintaining a Langelier saturation index of positive 0.3 to positive 0.6, predominated by calcium hardness, will do the trick. It's worked everywhere where people have had the courage to use it. Also, too, high calcium levels don't cause scaling. High temperature causes scaling. High pH causes scaling. You could have a lot of calcium dissolved in water, and as long as you're not kicking that pH up higher than it should be, or you're not heating it hotter than it should be, that calcium will stay dissolved. Other big thing, and we have offices throughout the western U.S. and in Texas. Place to place to place, this changes. I see up in the Pacific Northwest that they get away with water chemistry that in Southern California they could never, ever get away with because the source water's different. That makes such a big difference. And I had 3 different corrosion experts tell me that's the biggest problem that we're dealing with, is our source water being different from place to place, coupled with chloramine. Also, too, that this corrosion is not a material-specific thing. It's not a manufacturer-specific thing. It's a water thing. Water running inside a metal or sitting inside a metal. And over the past 30 years, the way we build our pools has changed, and the regulations that the source water, the drinking water people maintain has changed too, quite a bit. Now they're going to start going after calcium even more, is what I'm hearing is the next step in the EPA. So it becomes even more important. So if you have any of these issues, or you hear of people having any of these issues, you might want to take a look at the Reisner Index. It's worked well for us. It's a good tool, one of many tools that I have to use to help keep the people I work with, keep their equipment running as long as it should be. As I said in the beginning, my goal is to make that equipment last forever. I can't do that, but I will keep it running with your help as long as it can run. Thanks.